First page was all about a reading exercise. So we've got this function, capital F of x is 5x squared and a cosine of 3x. So in this problem, there are two instances of x. There's x in the 5x squared part. There's x in the cosine of 3x part. So we're going to use a product rule. So this is going to be a product rule. Because there's a function of x here and another function of x. A function of x is 5x squared. The other function of x is cosine of 3x. So our f prime will take the derivative of the first times the second plus the first times the derivative of the second. Derivative of cosine is negative sine of 3x. Derivative of 3x is 3. So here is just laying out all the parts in the product rule. If we want to clean this up, we have to recognize that there are two terms here, not three terms. There are two terms here. This 5x squared is getting multiplied by this negative sign. So we can say 10x cosine of 3x minus 5 times 3 is a 15x squared times a sine of 3x. Problem 1 was a product rule problem. Problem 2 is a chain rule problem. I take the x squared and I apply the square to the cosine. So in g of x, we're looking at 5 cosine squared of 3x. The way to read this, 5 cosine squared of 3x, there's only one instance of x, so we know that whatever's happening, it's a chain rule. No product rule here because there's only one instance of x in the whole problem. We can read this as 5 times the cosine of 3x squared. When you rewrite the cosine squared to be the cosine squared, you need an extra set of parentheses. Some of you rewrote this and wrote cosine of 3x squared. That's the cosine of the square of 3x, not the square of the cosine of 3x. So if you're going to use this strategy to help you see the chain rule, you need to be careful with your extra set of parentheses. So G prime, this is a chain rule problem. The derivative of 5 times something squared is 10 times that thing to the first times the derivative of that thing. In this case, the derivative of cosine of 3x is negative sine of 3x times 3. I need parentheses around that second, that derivative of the inside because it has a negative. So I need to be extra careful. Otherwise, it'll look like two terms. We're doing a chain rule, not a product rule. We're only going to have the two terms. Or sorry, we're only going to have the one term. We can clean this up. 10 times 3 is 30. There's a negative cosine of 3x and sine of 3x. In h of x. H of x, we've got another chain rule problem. I just moved the square inside, so I've got 5 cosine of 3x squared. Here, I just moved the square inside. I had the square moving from a factor to squaring the cosine to being the argument in the cosine. So this is just another chain rule problem. The derivative of cosine of a thing is minus sine of that thing times the derivative of that thing. So that was the read on the first three problems, just remixing a 3x, remixing 3 multiplied by 3 square, cosine, and times 5. This one, 5, was just benched the whole time. It was always just a constant multiple. A quick note on reading problems as a product rule. When I say the first one is product rule and the second and third one were chain rules, it doesn't mean that we can't apply the product rule to like the second and third problems. But one of the factors is 5. If we say the first factor is 5, the derivative of 5 is 0. So that wipes out one of the terms. So we can use the product rule. It's just excessive to use the product rule. At this point, I'm not concerned about that. But if it keeps going, then I have to throw a flag, call a foul, excessive use of math. So right now, that's not a problem. But later on, there'll be a foul for excessive use of math. You don't want to use the product rule when you don't have to. That really comes into play on something like problem D. In part D, we have P of X is 6 over x squared plus 1. In this problem, the numerator is just a 6. So we can use the quotient rule, but we don't have to. So we can read this problem like a quotient rule. Or we can just read it as a chain rule. Quotient rule is not really a necessary way to do this problem because the derivative of the top is 0. That's going to take out one of the an entire term. So quotient is a little excessive because the derivative of the top is 0. Because this happens. When we say the derivative of the top, we get 0. If we did the quotient rule, though, we'd say the derivative of the top is 0 times the bottom, minus the top times the derivative of the bottom, divided by the square of the bottom. So the derivative of the top being 0 should take out that first term. That's why it's important that we use parentheses. Some of you use the 0 to take out the x, but let the 1 escape. Some of you just let the multiplied by 0 and use the 0 like a 1. So this works out to minus 6x squared minus 6. Reading the problem as a chain rule problem, we would just say minus 6 times x squared plus 1 to the negative 2. I put the derivative, I didn't write the derivative at the bottom. And I let being distracted by that make me do the second part wrong. Sorry, the derivative of the top times the bottom minus the top times the derivative of the bottom, which is a 2x. all over the bottom squared. So when we simplify it, we get negative 12x over the square of the sum of x squared and 1. Reading this problem as a chain rule, we would say negative 6 times x squared plus 1 to the negative 2, and then we would multiply by the derivative of the inside, which is a 2x, which it gets us the same negative 12x over the square, x squared plus 1 squared. In Q of x, we definitely do need the chain rule, the product, the quotient rule, in as much as we ever need the quotient rule. Problem is given to as a quotient, so we could use the quotient rule. In this case, the derivative at the top is a 6 multiplied by the bottom. The bottom is x squared plus 1, but it's not just 6 times x squared plus 1. If we have 6 times 12, it's just not 62. It's 6 times the 10 and 6 times the 2. We have to use the distributive property. We need parentheses. Minus the top times the derivative of the bottom. That one's only one term, so. So the 6 has to get multiplied by x squared and 1 because distributive property, that's just how numbers work. So we get 6x squared minus 12x squared is negative 6x squared plus 6 over x squared plus 1 squared. That's probably our most popular expression for this answer. This class does not seem to be averse to have leading negative leading coefficients, so we'll just run with that. This is not the only way that we could have proceeded with this problem. We could have also read this as a product rule problem. And we just combine it with a chain rule. So we could write this as 6x times x squared minus 1 to the negative 1. So it works as a quotient. Or a product. We take the derivative of the first times the second. Plus the first times the derivative of the second. There are a few semesters in my calc history where I really tried to sell not quotient and forced product, and no one liked it because it ends up with things like this. But then we have to do if we do algebra, that will lead to the thing. All you have to do is get a common denominator. So this we could write as 6 over x squared plus 1. And then all this together, the only, we have a minus. The denominator is x squared plus 1 squared. And the numerator is 6x and 2x, or 12x squared. So to get a common denominator, we would just need to multiply by an x squared plus 1. I guess those are the dots. And once again, we would need our friend, the distributive property. Six times 12 is not 62. I don't know why I spent time doing that. No one did this. Everybody was involved quotient rule to varying degrees of success. So this one we could read as a quotient rule. Or we could just read this as terms. We can use our friend the distributive property and write this as x over 6 plus 1/6 x to the negative 1. As a quotient, we would take the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the square of the denominator. When I write 6x squared, I'm only squaring the x, but that is not what we need to do in this case. I need to square that entire denominator. And we fix that with parentheses. So we write 6x squared. There's no way to say it. It doesn't come out when you speak it unless you speak it right. It's the square of 6x. The square of the product of 6 and x. Biggest problem here was that the x squared minus 1 is being multiplied by a negative 6. We need parentheses around the x squared minus 1. Both of those terms are going to be negative. We don't subtract 17 by subtracting 10 and adding 7. So you get 12x squared minus 6x squared minus 6. And then we can write this as 12x squared minus 6x squared is minus 6x squared minus 6 over 36x squared. Spelled 6 wrong. And then we can drop a 6 because there's a 6 in all of the factors. So we could write minus x squared minus 1 over 6x squared. Oh, it's not negative 6. Sorry, it's positive 6. So it's x squared minus 1 over 6x squared. This is the same thing we get if we read it, if we use the distributive property and read it as terms. The derivative of 1/6 x is just 1/6. The derivative of 1/6 x to the negative 1 is minus 1/6 x to the negative 2. This looks different than our previous answer, but it is in fact the same if we do some algebra. If we rewrite this as 1 over 6 minus 1 over 6x squared and get a common denominator, then we're back to the same thing. Biggest problem on this page, the biggest source of missed points was the distributive property. And then number 2 was canceling things. So be careful about what you cancel. So let's see. For example, I don't want to cancel a 6x out here. Even though I see a 6x on the top and a 6x on the bottom, this 6x up on top is not a factor of the numerator. We only cancel factors. We can't cancel terms. So if I have 5x times 2x minus 3 over 5x. 5x is a factor, we can cancel it. When you want to cancel something like that, you have to remember what the canceling is. It's not just seeing a thing on top, seeing a thing on bottom, and getting rid of it. That's just visually what's going on. But that's not conceptually what's going on. I have multiplied by 5x, and I have also divided by 5x. That means I can skip that step. So if I have an expression that says 5x plus 7 over 5x, when you want to cancel something, you have to think, how is that thing included? Is it included with multiplication? Because that's what this particular brand of canceling means. So the 5x is not a factor. That 5x is not a factor of the numerator. In this problem, this 5x is a factor of the numerator. That 5x is a factor of the numerator. It is included by multiplication. It's 5x times some stuff. The 5x in the 5x plus 7 is not a factor of the numerator. We don't cancel factors, we only cancel terms. The only reason for this is that that's what numbers do. All the rules for algebra are only in place because that's what numbers do. So if I had 50 times 17 divided by 50, I've taken 17, I've multiplied it by 50, and I've divided by 50. Those are inverses. I'm going to be back to where we started. 50s cancel. But in 5x plus 7 over 5x, this looks like a 57 over 50. We don't get to cancel the 5s. We don't look at this and say, cancel the 5s. Our instinct wouldn't be to do that. But there's like a disconnect. There's a disconnect once the problem becomes abstracted into this algebraic form, and we just see stuff on top and bottom and we get rid of it. Don't cancel because of visuals. We have to read what's going on. Any questions? It's one of the things that makes math hard, because we can't read it with this big gigantic plus or minus going around. English just works that way. English is stupid. And we're wired to look for things that are close enough. Most of these expressions, when I've been writing them, I have been reading them completely incorrect, mathematically. And the only reason that y'all are able to write down the things that I've been saying when I've been reading these expressions is that I'm writing them right in front of you. So you're watching them be written. That makes sense? English is stupid. English is just like, man, I don't know, you'll figure it out. But we can't play that game with math. We have to make sure everybody reads the same thing. Like, how do you pronounce this word? How do you pronounce that word? Not your question. How do you pronounce that word? With a lowercase p. Polish, right? So, but if I write an uppercase p, right? Now what do we say? We say Polish, right? So if I put it in a sentence, we would say Polish the silverware, right? Oh, no. It's like, fuck you, English. At least in math, our symbols mean something. which is part of the problem. We learn things too much visually. And I'm not sure how to fix this problem. I don't know how to fix this problem. I don't know how to say cancel stuff and like make sure that students understand we cancel things when they are factors. We too often default to just see the thing on top, see the thing on bottom, get rid of it. And so we see the thing on top, see the thing on bottom, we get rid of it. We ignore the context and we just get rid of it. This does happen in English a lot too, because we grab little pieces and we just grab off little pieces, like a few bad apples. A few bad apples. Oh, it's just a few bad apples. What do a few bad apples do? What's the rest of that phrase? A few bad apples spoil the barrel. So what that means is that if you find a few bad apples, the whole barrel is trash. And we've ended up taking that phrase, cutting off part of it and using it completely incorrectly, the opposite of its intent. Because we just grab a little piece and decide it means something else. In certain cases, this is like valid. Everybody familiar with the road not taken? 2 roads diverged in a wood, and I took the one less traveled, and that's made all the difference. How do we interpret that now? We interpret that to mean like, oh, follow your own path. Take the road less traveled. Is that what the intent was? If you ask him about it, you can't because he's dead. So I don't know, get your Ouija board. It's like, oh, dude, that's not what it meant. I meant it's like, oh, don't worry about the small things. Don't sit there and like, it's like, oh, which one should I do? Which one should I do? Which one should I do? This is really important. It's like, oh, it doesn't matter. Just go. Just fucking go. He was trying to say, just fucking go. And we're like, oh yes, forge your own path. And what's that got us? Fucking individualism. It's like, oh, I should be able to do what I want. But dumb fuck, we live in a society. We get to stop you. You know what I mean? I should be able to drive 120 miles an hour. It's like, oh, no, we have decided that you don't get to do that. Who's we, the government? No, it's like us. We collectively as a society have decided that's unsafe. You don't get to do that. I don't care how good a driver you are, because first of all, you're wrong about how good a driver you are. Any questions? We just like start truncating things and like decide it means something else. And that happens all the time in English. There's a lot of phrases that we walk around with that don't mean what they originally intended to mean. In some cases, sorry, dude, that just means that now. So sorry, Bob, that just means that now. It just means we should follow our own path. Fuck, that's just going to lead to more individualism. I know, but here we go. And then the same thing, we apply that kind of thinking that happens when we come across math. Because when we see things like the distributive property that I've been talking about today, it's like, ah, yes. And we even have our international symbol for the distributive property. This is AB plus AC. But what is the most important thing that I didn't say when I wrote this down? Oh, no, this is the distributive property, right? I left off a critical fucking piece of information. I left off what's going on between A and those parentheses. The most important part of this little expression that we've summarized this way is that this is with multiplication. The most important part is this thing right here. A times B plus C is A times B plus A times C. Multiplication distributes over addition. But the problem is we just see the parentheses and we have this visual thing. It's like, oh, something in front of parentheses, do that to all the stuff inside. And then so when we have something up here, like natural log of B plus C, we're like, oh, dude, I've seen this shit before. It's natural log of B plus natural log of C. And that's just not true, because that's not natural log times B plus C. It's natural log of B plus C. So it's like, oh, nope. And the reason for that is that this is not multiplication. We can't just leave off a part of our expression and just go with what it looks like. Make sense? A few bad apples spoils the bunch. Yeah, a few bad apples leads to an incorrect interpretation, leads to bad policy. Any questions? Comments? Snide remarks? I know it was just it's a reading exercise that we dealt with on this test. That's why I'm bringing this up. We have to be careful about how we read things. One of the minor things that came up, this that I'm just thinking about now, speaking of reading things. When we're taking derivatives, the arguments of your derivatives of your trig functions won't change. If you have a sign of, if you have something that has a sign of 3x, there should always be a sign of 3x and cosines of 3x. That 3x inside, the cosine and sine, will not change. We have to back up into trigonometry if we want to change the arguments inside of our trig functions. But for calculus, calculus does not care about what's going on inside the trig functions. It's always going to be the same. So don't let that change. Also, if you write sine just by itself, that doesn't mean anything. Sine of what? Sine is only half a sentence. Any questions? Comments? Deep thoughts? Snide remark. There's a Canvas version of practice test 2 where you can enter your 6 derivatives. I guess you know what they are now, but if you're just going to take these and copy them over into Canvas, I mean, fuck, I can't fix that. I mean, if that's all you're going to do, then I can't fix that. So use this to practice, learn how the reading goes. That's it for today. That's it for this week. We'll do some more definite integrals on Monday. Come and pick up your practice test 2 if you have not, and sign in on the sign-in sheet wherever it may be.